Hello, am I audible? Am I audible? Okay, we would be solving the numericals of entropy change. Okay, to see that the concepts of entropy they are internalized. We had solved two numericals yesterday involving a copper block which was immersed in the first numerical. We talked about a copper block, which a copper block was immersed in a fixed quantity of water, and in the second case we talked about the copper block which was immersed in a big reservoir, that is lake. Okay, and in both the cases we found that the entropy of the copper block was decreased, and the entropy of the water reservoir, right, was increased. Okay, and overall the entropy of the universe we found to be increasing. So what insights we get from that? That is, we get to quantify the irreversibility during the heat transfer process. So that is the idea of solving this numerical feel of why this entropy change calculations are important. Okay, so today I will be solving one or two more problems. Okay, and let me share with you. Let me close the poll now, and let me share with you the whiteboard. Okay, so allow me 1 or 2 minutes for sharing the whiteboard. Okay, and you need to tell me whether the whiteboard is visible to you. Okay, just a minute. Okay. You tell me now, Ganesh or somebody, whether the whiteboard is seen. Okay. Whether the whiteboard is seen. Okay, thank you, Sushant. Okay, okay, thank you, Gargi, Vedant. So take down the numerical. I'm dictating also, and I'm writing it on board. So so right now, consider 1 kg of ice, 1 kg of ice, which is at -5 degrees centigrade. Okay, consider 1 kg of ice, which is at -5 degrees centigrade. Degree centigrade, and what is happening to that ice? So that ice, which is at -5 degrees centigrade, is kept exposed to the atmosphere surrounding. Okay, is exposed to the atmosphere that is surrounding, and let us say that the surrounding is at a temperature of 20 degrees centigrade. Okay, is exposed to atmosphere which is at 20 degrees centigrade, atmosphere which is at 20 degrees centigrade. Okay, and so which is at and gradually it comes and it attends. Okay, and comes in thermal equilibrium with the surrounding. Okay, it comes into thermal equilibrium with the atmosphere, comes into it means that the temperature will become 20 degrees centigrade. That's it. It would melt and it would become water, and that water would then finally attain a temperature of 20 degrees centigrade, because that water would now comes into thermal equilibrium with the atmosphere. So the question is, and we will solve it in steps, and you should also answer it, right? So first thing is, you need to calculate what is the heat transferred from the atmosphere to the ice. Okay, what is the heat transferred from the atmosphere, okay, to the ice, okay, as it melts to water and gets converted to 20 degrees centigrade water. Okay, heat transferred from and okay, of the right, because calculations you need to have certain data. Let us say that Cp then of 333 per kg. Okay. So first you solve the first part of the question and tell me the answer. Okay, and then we'll go to the, so calculate this first and tell me the answer. Calculate this first and tell me the answer. Whether you have copied down the question, you have copied down the question. So whether the question is copied down, yes or no? Tell me whether you have copied down the question. First calculating the heat transfer. Let me erase the it is kept in the atmosphere. Ice is kept in atmosphere, is at which is at 20 degrees centigrade. There is sensible heating. There is a sensible heating of ice. Okay. Then what happens next is ice would melts. So ice at 0 degree centigrade would get converted to water at 0 degree centigrade. Okay. So this is latent heating. This is latent heating. Then what happens next is this water heats. Okay. So water at 0 degree centigrade gets converted to water at 20 degree centigrade. So this is sensible heating of water. Okay. It means that if you want to calculate this Q, so let this be Q1, this be Q2, and this be Q3. So the heat transferred Q, okay. So this Q is Q1 plus Q2 plus Q3. Okay. So now what is Q1? Q1 is mass of ice into Cp of ice into delta T. So delta T would be 0 minus of minus 5. Okay. What is Q2? Q2 is equal to mass of ice into latent heat. Okay. So this is equal to 1 into 333.3. The Cp of ice is given to be 2.093. Okay. And what is this Q3? Q3 is mass of water, which is same as mass of ice. Mass of water is same as mass of ice into Cp of water into delta T, where Cp of water is 4.187 kilojoules per kg Kelvin, and this delta T would be 20 minus 0. Okay, this mass of ice is equal to mass of water is equal to 1 kg. Okay, so you'll get the heat transfer as, and yes, Kunal, you are correct. The value you have obtained is correct. Okay, so Kunal has got it correct. So that this quantity Q heat transfer Q, the answer is 427.5 kilojoules. Okay, so this you need to be very clear. I hope you have understood the first part of the problem, how to calculate the heat which is transferred from the atmosphere to the ice, which is at minus 5 degree centigrade, as the ice gets converted to water at 20 degrees centigrade. Okay, I hope it is clear to you. Can I rub the board now? Can I rub the board now? Kunal, can I rub the board? Should I rub the board now? Okay, so let me now erase the board and let me find the entropy change of the system now. Okay, entropy change of the atmosphere and entropy change of the system. Okay, so let me erase this. Let me erase this. I'm clearing this canvas now. Okay, and let me calculate now. So this is your ice at -5 degrees centigrade, which is your system actually, and your atmosphere is at how much? 20 degrees centigrade. 20 degrees centigrade. So let us first find the entropy change of atmosphere. So what will happen to the entropy of the atmosphere? Whether it will increase or decrease. What will happen to the entropy of the immediate atmosphere, which is surrounding this immediate atmosphere? Whether it will increase or decrease. Whether it will increase or decrease. Why? Whether it will increase or decrease, you try to answer this question, and why. What will happen to the entropy of the surrounding? Entropy would increase or decrease? Or decrease, and why? Connectivity, but I would continue with my lecture. Okay, so the entropy of the atmosphere would decrease. Okay, atmosphere would, why it would decrease? Because heat is lost. Heat is lost. Okay, so how to find that entropy of the atmosphere? Entropy change of the surroundings, integral of minus del Q by T. Since temperature of surrounding is constant, temperature of surrounding is constant. Yeah, it will decrease, correct. So delta S of the surrounding, is equal to minus integral of del Q one upon T. This is outside, temperature is constant, which is nothing but, okay. So this Q we had already calculated, Q lost by surrounding. Okay, so Q lost by surrounding is minus, it is 427.5 kilojoules. Okay, and this temperature of the surrounding is 20 degrees centigrade. Temperature of the surrounding is 20 degrees centigrade plus 273, that is 293. which comes as minus 1 Kelvin. So entropy of to ice, which is giving the heat to ice, okay, decreases because of this heat transfer, by 1.46 kilojoules, 1.46 kilojoules per Kelvin. So this is the decrease in the entropy of the surroundings. Okay. Now let us calculate the entropy of the calculate entropy change of system. Entropy change of system. System is what? System is the ice getting converted to water. So calculate this. How will you calculate this? So let me erase this. I hope this is written. You have copied this down. Entropy change. I'll just repeat this. What we have calculated. We have calculated the entropy change of the surrounding as minus Q upon T. So Q we had already calculated. Q is the heat which is lost by the atmosphere, and that becomes minus 427.5 kilojoules. Okay, which we had calculated in the first part of the problem. Now the entropy change of the surrounding is minus Q upon T. Why this expression comes? This is because your surrounding would act as a sink. Okay, surrounding acts as a sink and its temperature remains constant. Temperature is constant at 20 degrees centigrade in spite of heat transfer. That is because it acts as a reservoir. Okay. So we can take this expression as minus Q by T, and hence we can calculate it as minus 1.46. Okay. So now let me erase this and let us calculate the entropy change of the system. Okay. So I am erasing this now. Okay. So now this is ice. I want to find the entropy change. Okay. So let us say this is delta S of system. So this will be equal to entropy change of the system when ice is heated to ice. Ice is heated to ice from minus 5 degrees centigrade to 0 degree centigrade, plus delta S of the system when the ice melts, plus the delta S of the system when this water at 0 degree centigrade is heated to water at 20 degree centigrade. Heating of the water. So let me call this as delta S1, delta S2, and delta S3. Okay. So delta S of the system is entropy change when the ice is sensibly heated from minus 5 degree centigrade to 0 degree centigrade, plus the entropy change during phase transformation, that is ice to water. Okay, and then entropy change during sensible heating of water from 0 degree centigrade to 20 degree centigrade. Okay, so first let us calculate the delta S1. So this will be integral of del Q by T. Okay, what are the temperature limits? Temperature limit is -5 degree centigrade up to 0 degree centigrade plus 273. Don't forget to write this 273. It is very important. Plus 273. Okay, so this becomes integral of, this is 268, this is 273 Kelvin, and this is m Cp of ice dt upon T, which becomes equal to m Cp of ice ln log to the base e T2 by T1. That is T2 by T1 means 273 upon T1 is 268. This is 1 and this is how much? 2.093. So tell me this answer. Tell me this answer. How much is this? How much is this value? Delta S1. Tell me this value. Delta S1. Yuvraj, Kunal, Shubham, Ganesh, Shreyas, Maheshwari, Gargi, Vedant, Chaitali, Sushant. Okay, Kunal has calculated and Kunal has got it right, I guess. Yes, just check whether it's 0.0389 or 0.0386. Kunal, just check whether it's 0.0389 or 0.0386, whatever. Okay, check this value. 0.0386. Oh, all right, 0.0386. So Ganesh is also getting the same answer. So Ganesh and Kunal, you are right. So let me write down that answer. 0.0386. Okay, 0.0386. So this is delta S1. Okay. Now let us find delta S2. So delta S2 is what? Delta S1 was basically during sensible heating of ice. Okay, sensible heating of ice. Okay, now we need to calculate what would happen to this entropy change during melting of ice. Okay, melting of ice to water. Now you have studied in physics that this melting would happen at constant temperature. Okay, so this melting happens as constant temperature, so this temperature remains constant, so it would be Q upon T. Okay, and this Q is the latent heat of fusion. Latent heat of fusion of ice. Okay, and this T is your melting point. This T is your melting temperature. Okay, melting point, melting temperature. Okay, so this comes as how much? Q is given as 333.3 upon what? Upon what I should do? Maheshwari, what should I do? Upon what? 333.3 divided by what? Anybody? 333.3 divided by what? Correct. Kunal is right. So we need not make the mistake. Okay, it should be 0 plus 273. Okay, you should not put it as 0. Okay, so this is 273. So this comes as this. Obviously, what is that value? Is it 1.22? Is it 1.22? How much is this value? How much is this value? 1.22. Ganesh, right. Thank you, Ganesh. It is 1.2. Okay, 22. All right. Thanks, Ganesh. Sharvari, thank you. Sushant has also got it. Almost all of you have got it. So it's not a difficult thing. Pranav, thank you. Akanksha, everybody. Now the third is the entropy change. Now third is the entropy change. Entropy change of the system when this water gets heated. Okay. When the water gets heated sensibly, sensible heating of this water which is at 0 degree centigrade to water, again it remains water at 20 degree centigrade when it comes in thermal equilibrium with the surroundings. So this ice is going to be converted to water finally, which is at 20 degree centigrade. Okay, so this ice gets converted to water from ice at -5 degree centigrade to water at 20 degree centigrade. Okay, so this is again, now you must have guessed how to calculate this. Okay, so it would be m Cp of water. Now mind well, Cp of water dt by t, the limits are 0 degree centigrade, there is 0 plus 273, and 20 degree centigrade, that is 20 plus 273. Okay, so which becomes m of water, Cp of water log to the base e, which is 293 upon 273. Tell me the answer now. How much is that value? How much is that value? So what is the value you are getting here? As the water gets heated from 0 degree centigrade to 20 degree centigrade, how much is that? Okay, Sharvari, thank you. It is 0.296. Okay. So these three, if you add these three, you will get the entropy change of the system. Entropy change of the system. Okay. Add this and you'll get the entropy change of the system. Okay. And then what we need to do is that you had already calculated the entropy change of the atmosphere. Entropy change of the atmosphere to the entropy generated, or it is the entropy change in the universe. It is the entropy generated in the universe because of irreversible heat transfer. So for finding the answer now, what you need to do is that you need to total this up and calculate delta S of system. Total this up, calculate delta S of system, and add that to the delta S of the surrounding. That is the delta S of the atmosphere. What you'll get is the delta S generated in the universe. Okay. So find that now. Find that. I hope I can rub this. Okay, let me erase this a bit. Okay, I'll not erase it completely. Let me partially erase it. Okay. So what you need to do now is I would be writing what you need to do now. Okay, right. Okay. So you see now that delta S of the universe is equal to delta S of the surroundings plus delta S of the system. And what is this delta S of the system? That is 0.0386 plus 1.22 plus 0.296. And what is this delta S of the surrounding? You had calculated that earlier as minus 1.46. Okay. So you give me this total. This total is how much now? Give me this total. It would be a positive value, obviously. Give me the total. What is that value? Delta S of the universe. Delta S of the universe. Anybody who has got the answer? Delta S of the universe is how much? Okay, Sharvari is getting it as 0.0946. 0.0946. Anybody else apart from Sharvari? Okay, thank you, Sharvari. So the answer is 0.0946. So tell me, what does it tell you, Sharvari? What does this tell you? 0.0946 kilojoules per Kelvin. So what does this tell you? What is the meaning of this? That the delta S of the universe is 0.0946. What is the meaning of this? Whether there is a heat loss in this, and that is the reason why the delta S of the universe is 0.0946. What is the reason why you are getting the delta S of the universe as 0.09? Anybody? How to make sense of the numbers? Anybody? Yes or no? The meaning is because the delta S of the universe is positive. Okay. So why has the delta S of the universe changed? Why has the delta S of the universe changed? And why it is a positive quantity? The delta S of the universe has changed because the heat transfer from the surrounding to the ice, as the ice melts from minus 50 degrees centigrade and it comes in thermal equilibrium with the surroundings, that process of heat transfer is an irreversible heat transfer. Okay. Correct. Vedant is correct, because the process of heat transfer is irreversible heat transfer. Okay. Yes, Gautam is right. The reason we have quantified. So what we have done is that by calculating the entropy change in the universe, which is nothing but the entropy generation in the heat transfer process, the heat transfer in the heat transfer process from the surrounding to the system, the process being irreversible, the entropy change is positive. What would have happened if the process was reversible? What would have happened if the process was reversible to the entropy change? What would have happened if the process was reversible to the, what would have been the value of delta S of the universe? What would have been the value of delta S of the universe had the process been reversible? The answer is the value of delta S of the universe would have been 0 in case the process was reversible. If the process was reversible, the delta S value of the universe would have been 0. Okay. Delta S value of the universe would have been 0. What if the value of delta S, we had got the value of delta S of the universe as negative? What would have been your comment? If the value of delta S of the universe was negative, what would have been your comment? Was negative. The comment would have been that such kind of heat transfer phenomena impossible. Such kind of heat transfer is impossible. Okay. So this you need to understand that we are basically talking about the principle of increase of entropy, okay, of the universe, which we said that what it is the entropy of the universe, okay, would always increase if the process is irreversible, and by how much it will increase would depend upon the extent of irreversibility. By how much it would increase would depend upon the extent of irreversibility. If the irreversibility is more, the entropy change of the universe would be more. If the irreversibility is less, the entropy change of the universe would be less. Okay. So as you tend towards the reversible process, the entropy increase of the universe would tend to zero. Okay. So ideally, we are expecting that the entropy change associated with the process, okay, entropy change of the universe, whenever a process happens, ideally we are expecting that the entropy change of the universe should be zero. That is our ideal. Okay, but in practice you'll find that that value is always positive. Okay, but as engineers our attempt should be to minimize the entropy change of the universe. Okay, so when we are able to get certain value, okay, for example in this case, if you had got a value of 0.0946, okay, kilojoules per Kelvin is the entropy change of the universe. So as engineers, if we can strive towards reducing this entropy change from 0.0946 to, let us say, 0.06, okay, so then it is an achievement. So we have done some engineering job, okay, and we are now reducing the irreversibility of the transaction. Okay, I hope you understood this concept. So basically the beauty of this concept of entropy is that, and by calculating the entropy change, we are in a way quantifying the irreversibilities in the real life. Okay, in the second law of thermodynamics we are always bothered about a reversible process and irreversible process. We talk about reversible engines, irreversible engines, but all this talk of second law, these are in qualitative terms. Okay, in qualitative terms, right? If you want to quantify this, because engineering is always about measurements, it's about quantification, then this property of entropy, which was discovered, okay, as a logical end of second law of thermodynamics, and we are talking about the discovery of entropy property, that property of entropy aids us in quantifying the irreversibility. I hope you understood this. Okay. So in the next class, I would be Okay, thank you very much and meet you in the next class. I'm closing the webinar for today. Thanks a lot.